I said, excuse me, the series test that we've had so far only dealt with the terms that were positive on your series. This section deals with what we call an alternating series, where every term alternates between positive, negative, or it can be negative, positive, it doesn't matter, but the terms alternate in signs. So if your terms alternate in signs, and if you look at the b sub n's, forget the negative ones, but if you look at the b sub n plus 1 compared to b sub n, if it is decreasing for all n, and if the limit as n approaches infinity of your b sub n is equal to 0, then your alternating series converges. If it does not meet these two criteria, you have to try another test. An example. Number 6. N equals 0 to infinity. Negative 1 to the n plus 1 over the square root of n plus 1. All right, this is an alternating series, so you cannot use the comparison test, even though it looks similar to something you might have wanted to use the comparison test on. So what you decide, if this is an alternating series, try your alternating series test. Look at 1 over the square root of n plus 1. That is your b sub n. B sub n plus 1 is 1 over the square root of n plus 1 plus 1, which is 1 over the square root of n plus 2. So you need to look and see if 1 over the square root of n plus 2, that's your n plus 1 term, is that less than or equal to 1 over the square root of n plus 1. Decide if that is decreasing. If you need to, you can cross multiply. Is the square root of n plus 1, is that going to be less than or equal to the square root of n plus 2? Yes. This is true. Second thing you look at is the limit as n approaches infinity of 1 over the square root of n plus 1, the limit of the b sub n term. See what that limit is. In this case, as your denominator gets larger and larger and larger, your fraction is getting closer and closer to 0, so the limit is 0. Since condition 1 is met and condition 2 is met, you can say that your series is convergent by the alternating series test. Question. Let's look at number 8. Sum from n equal 1 to infinity, negative 1 to the nth, n squared plus n plus 1. Okay, this is an alternating series. But if you try to use the alternating series test, I'm going to jump straight to the limit, because I can tell that if I look at the limit as n approaches infinity of n squared over n squared plus n plus 1, that limit is not going to be 0. Do you know what the value of that limit is? 1. Since that limit is 1, I cannot use the alternating series test. I've just got to stop right there. And I have to think of something else to use. Well, everything else except the test for divergence has to have positive terms. So I need to look at the test for divergence. If you'll think back or look back at your notes, the test for divergence says I need to look at the limit as n approaches infinity of this entire thing, -1 to the n, over n squared plus n plus 1. I need to look at that entire limit with the -1 in there and everything. All right, well, think about this limit. This part is still going to 1. But as this gets larger and larger and larger, what's happening to this -1? It's alternating between a +1 and a -1. So this limit is actually going +1, -1, +1, -1, and it's never going to anything. This limit does not exist, which means by the test for divergence, our series diverges. Therefore, our series diverges because that limit does not exist. You can only use the test for, you can only use the alternating series test if your series is decreasing and if the limit of the b sub n is 0. Yes?
When we do a problem like 2 through 4, just pick one of them.
Oh,
We have those on
sure.
homework.
Sure.
Any questions on me out?
Yes. Once where you get the patterns.
Yeah, they give you the number pattern.
Oh, what about, I don't know.
That's how they are on homework.
Yeah, what, number 4 maybe? I don't know. Whoop, there it is. All right, test the series for convergence or divergence. Okay, so we need some kind of formula. This is not a geometric series because nothing's multiplied times the 1 to get to the next one. So let's see if we can come up with something else. If n is equal to 1 to infinity, we have, it is alternating, so we have -1 to the n minus 1, I guess. And 1 over the natural log of something. How about n? Yeah, n plus 2. If that's 1, that's 2, 3, sure. 1 over n plus 2. Natural log of n plus 2.
If you have one that starts off positive, it's going to be n minus 1, but if you have one that starts off negative, it'll be just n negative.
Sure. Mm-hmm.
That's a good way of making it.
Yes. Yes. Okay. Need to see if this thing, you can test either one first. If you want to look at the limit as n approaches infinity of 1 over the natural log of n plus 2. What about this limit? All right, as you put larger and larger numbers in here, you're taking the natural log of larger and larger numbers, which is getting larger and larger and larger. So this fraction is going to 0. So there's condition 1. Second condition is the n plus 1 term. I have to put n plus 1 right there, which is going to make that n plus 3. Is that less than or equal to 1 over the natural log of n plus 2? If you want to cross multiply, you can. The natural log of n plus 2, is that smaller than the natural log of n plus 3? Yes, this is going to be smaller than this. Oops. Therefore, your series is convergent by your alternating series test. Do you want to do another one with the formula? Trying to get the formula? Do you want to do another one with the formula? Yes, you do. Okay, let's see. 2/3 minus 2/5 plus 2/7 minus 2/9 plus 2/11 dot 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 dot. Should be a minus right here.
I already know it's gonna be a negative 1 to the n minus 1 to start off.
Okay. We have negative 1 to the n minus 1. I know I got a 2 on the top. How about that?
Just thinking that.
Right. Now we got to get the 3, 5, 7, 9, 11. Those are odd numbers. 2 up. N plus 2. If this is 1, this is 2, this is 3, this is 4. 3 plus 2 is going to give you 5. Not going to give you 7. 2n, maybe 2n minus 1. Does that work? Or no, that doesn't work. Because that's, how about plus 1? I think you said plus 1. I think I heard minus 1, but I think you said plus. So that works. If n is 2, that works, that works, that works. Doesn't it? Yes, 9. So 2 over 2n plus 1. All right, so see if it meets your two conditions. Limit as n approaches infinity. 2 over 2n plus 1. Denominator's getting larger and larger and larger. The fraction is going to 0. Is 2 over 2n plus 1, the n plus 1 term, is that less than or equal to 2 over 2n plus 1? And again, if you want to cross multiply, is 2 times 2n plus 1 less than or equal to 2 times 2n plus 1 plus 1. Yes, this is true. Therefore, since it met these two conditions, your series converges. Remember, if it doesn't meet one of these conditions, you back up and you use something else. Usually it's going to be the test for divergence. Okay on this, you think? All right, now one thing we're going to look at here is how accurate is an estimate of the actual sum going to be. When you take a certain number of terms and add them together, if you added those first 4 terms for that series, you would get an approximate value for the sum. If you went out further, if you added, say, the first 10 terms, you would get closer and closer to the actual sum. If you added 100 terms, you would get even closer to the actual sum. But how much error is involved, okay, in what you do? Right? This is going to lead us to using the alternating series test estimation theorem. You can only use this when you have an alternating series that converges, that meets these two conditions. If you have an alternating series that is decreasing, the b sub n's are decreasing, and the limit is 0, then you can calculate how much error is involved in your guesstimate for the sum. The remainder, or the size of the error, the absolute value of the remainder, is the actual sum minus your estimate, which is actually less than or equal to the first term that you do not add in there. It is the first neglected term. Your error is less than or equal to the first term that you do not add in your sum. For instance, let me go back to this problem that I had a minute ago. If I add these terms, first 5 terms. The error, all right, the amount of difference between that and the actual sum is the absolute value of this term right here that I do not add in there. The error is going to be the absolute value. This is 1, 2, 3, 4, 5. This is the 6th term. Let's see, what can I call it? It would be v sub 6, which is 1 over the natural log of 8. That is the amount of error that's involved. Does that make sense? Sort of? It's just the next term. That's the error that's involved, the next term. And if I added the next term, then the error is going to be the next term, which is even smaller. And if I add some more terms, if I add 10 terms, the error is going to be the 11th term. It's got to be less than the 11th term. So the further I get out there, the smaller my error is getting. Okay? Because we're getting closer to that actual number. So what we're going to do is a problem like number 23, where we're going to figure out how many terms we have to add to get a certain amount of error. So in number 23, series from 1 equal n to infinity, negative 1 to the n plus 1 over n to the 6th. And they want to know how many terms, how many terms do we have to add so that the absolute value of the error is less than this number. How many? 1, 2, 3, 4. 4 zeros. 1, 2, 3, 4, 5. All right, now I can only use this method if this is decreasing. Is my n plus 1 term less than or equal to the nth term? Yes, that's true. Is the limit as n approaches infinity of 1 over n squared, into the 6, is that 0? Yes, it is. Because it meets these 2 conditions, I can look at the amount of error. To find the error, or the number of terms I need to look at, I need to look at the n plus 1 term, which is 1 over n plus 1 to the 6th. That's going to be the amount of error, if I can just figure out what n is. So take this, b sub n plus 1, and put it less than or equal to 0.00005. That number right there. This happens to be an equation that you can solve for n. To do that, I could cross multiply. That would be 1 over, let's see, what would I do? And I would divide, I would cross multiply and divide. I would get 1 over 0.000405 is less than or equal to n plus 1 to the 6th power. So multiply that over there and divide it by that. To get rid of this, I need to take the 6th root of both sides. So I have 1 over 0.00005 to the 1/6 is less than or equal to n plus 1. Subtract 1, and I have 1 over 0.0005 to the 1/6 minus 1 is less than or equal to n. You can put this in your calculator. And did I bring a calculator? Of course I did not. So, may I borrow a calculator, or could someone put that in their calculator? and get a decimal.
4.24.
Did y'all get that? Okay. That means n, the number of terms that I need to add, is bigger than 4.21. It has to be an integer because you're only adding 0, 1, 2, 3. So the next integer is 5. So that means I need to add 5 terms in order to get this amount of accuracy. So that this is the amount of error. You just take the next whole number above 4. All right, let me show you what you do when you have one like 25 where you get something you cannot solve. You have n equal 1 to infinity, let's see, negative 1 to the n minus 1 over n squared 2 to the n, and they want the absolute value of the error to be less than 3 zeros this time and a 5. All right, I can tell you that if I put n plus 1 over here, if I put 1 over n plus 1 squared and 2 to the n plus 1 is less than or equal to this. If I put that, that's going to get an equation I cannot solve without a great deal of difficulty because I've got a variable in my exponent. I mean, I could do it probably, but I don't want to. It's too hard. So what you can do is actually list out the first few terms and see if you can find the first one that is smaller than this one. So the first term, it doesn't matter about positive or negative. You don't need the positives and negatives. All you need, because you're looking at absolute value, I need 1 over 2. The next term is going to be 1 over 2 squared times 2 squared. The next one is going to be 1 over 3 squared times 2 to the third. The next one is 1 over 4 squared times 2 to the fourth. The next one is 1 over 5 squared times 2 to the fifth. And I'm just, for argument, I'll put the next one 6 squared times 2 to the sixth. And again, I didn't bring a calculator, but I would go, it's probably not one of the first few terms. I would just kind of go out here somewhere and pick one of these numbers. Put this in your calculator and see if you get a decimal that's smaller than the one you're looking at. Maybe this 1 over 5 squared, 2 to the fifth. See what kind of decimal you get. Anybody got something? Anybody got one?
0.000125.
Wait, how many zeros? 2 zeros and a 1? Okay. What about the next one? 3 zeros and a 4. Okay. 3 zeros and a 4. That's the first one that is less than this number. So I'm not going to add this one. I'm going to add everything in front of it because this one is less than this error. So I'm going to add 1, 2, 3, 4, 5. It looks like, again, I'm adding 5 terms. And the answer's not always 5. Just thought I'd throw that out there.